In this video, I'll be going over moments and leverage. In particular, I'll be focusing on the following three things: what moments and levers are, the principle of moments, and some simple examples involving moments. This is another weird topic, but I hope by the end of this video you have a better grasp of it. To start off, when a force is applied to an object that's suspended or balanced at a point, it's going to turn at that point. Think about the hands on a clock. If you were to push the edge of those hands, you'd notice that they turn around the centre of the clock. That's where the hands are connected to the clock mechanism. We can say that a moment is a turning effect of a force. If you apply a force to something that's connected to a pivot, the moment is a turning due to that force. So I've got my clock example here. If I push the big hand, clearly the hands will turn around the middle. Recall that's where we said that the pivot would be. We'd say in this case that the moment is acting in a clockwise fashion. In terms of maths, we can define the moment as the force multiplied by the perpendicular distance from the line of action of the force to the pivot. Now, it's not as complicated as it sounds. In symbol terms, we just say that m is equal to F multiplied by d. Remember, it has to be the perpendicular distance. For the units, force has the units newtons, distance has the units meters, and so the moment has the units newton meters. If you prefer to use a triangle method to rearrange your formula, this is what the triangle looks like. Now, I'm going to quickly go over an example of using this equation and how to apply it. I've got a wrench that I've been trying to unscrew some bolts with. That centre of the bolt is where it's turning from, so we can say that's the pivot. I apply a force at the tip of its handle. Imagine if you were to continue this force to an imaginary line. That imaginary line is what we would call the line of action. If we draw a line across from the pivot, we can find out the perpendicular distance. And you can see that distance is perpendicular to the line of action of the force. Perpendicular just means that it's at a 90-degree angle. Let's say that this force was 30 newtons and this distance was, let's say, 10 centimeters. We can calculate the moment by just taking these, putting them into the equation. So that's 30 newtons multiplied by, now it wouldn't be 10 centimeters because remember, the distance has to be in meters. So 10 centimeters is 0.1 meters. And this tells us that the moment is equal to 3 Newton meters. Remember, that's 3 Newton meters clockwise. Here's another example where we're using a crowbar to lift the side of a very heavy weight. The pivot's right at the bottom of the crowbar because that's where the crowbar is actually turning from. We apply a force at the top of the handle, and once again the perpendicular distance is on the line of action of the force to the pivot. Try having a go at doing this yourself, so just pause the video and have a little go now. Oh, it's really nice with that one, and it's simply 200 multiplied by 0.75. It's already in meters, so we don't need to convert it like we did last time. In this case, the answer is just 150 Newton meters. What happens if I were to apply the force near the centre? That moment suddenly becomes a bit smaller, so now it's only 100 Newton meters. Previously, we had 150 Newton meters, and that was at the 0.75 meter point. What we can say is that as you move closer to the pivot, that turning effect of the force applied gets smaller. We went from 0.75 meters to 0.5 meters, and the turning effect went from 150 Newton meters to 100 Newton meters. The further away you are from the pivot, the more you can magnify that force. That was a simple example of a lever. Levers are used when large forces are required. Levers magnify the applied force by taking advantage of the principle of moments. The easiest way to explain what the principle of moments is just to go over a basic example. So here I've got a beam with two forces being applied on either side. It's sort of balanced on a pivot. These forces are different and the distance between them is also different. What I can tell you is that this beam is completely and perfectly balanced. To show you that, let's just consider the left-hand side for now. Remember, the pivot is the tip of that triangle. If we apply a force on this end, the beam is going to want to turn anti-clockwise. The moment for that is equal to 6 newtons multiplied by 2 meters, and that gives us 12 newton meters. Now if we do the right-hand side, we can see that the beam will want to move in a clockwise direction. The moment on this side is 4 times 3, which gives us 12 newton meters. Remember that this side is anti-clockwise and this side is clockwise. And they are both exactly the same. If we have a moment of 12 newton meters anti-clockwise and a 12 newton meter moment clockwise, we can just say that it's balanced. Both sides are equal to each other, nothing is going to happen. So we can say that in equilibrium, the sum of the clockwise moment is equal to the sum of the anti-clockwise moments. Now I use the word sum because sometimes you can get more than one force acting on each side of the beam. So I've covered quite a bit in this video. I've gone over moments and levers, what they are used for, and applying them to some examples. An important tip I will leave you on is this. Using the moments equation, m equals force times distance, the distance must be perpendicular distance always, between the line of action of the force and the pivot. A lot of people get tricked out by this. The perpendicular distance, what does it mean? So make sure you understand how to figure that distance out.